Actually, in grade 11s, we're going to finish off this week talking about a few last relationships for gases, and we're going to be talking today about ideal gases and the ideal gas law. Okay, where we are in your textbook is 12.2, page 582 to 589 if you're confused. So we're going to start off by doing a quick review of the laws that we learned in activity 1 and activity 2. Then we're going to learn about the difference between an ideal gas and a real gas and practice using the ideal gas law and do some practice problems together. And then you'll have a chance to do some homework problems. And just like you've been doing so far in the course, since we've been in distance learning, you can submit those practice problems either in the document or with a picture taken of your hard copy notes. Okay. So by the end of the class, what we should be able to do is compare and contrast real and ideal gases and also complete calculations involving the ideal gas law. Now, we've learned three gas laws this week so far, and the combined gas law, which combines all three of those gas laws together. So the first one we learned was Boyle's law, which is how pressure and volume are related. P1V1 equals P2V2. And what we said is volume and pressure vary. This button, or this symbol, right here means like vary or changes with an inverse relationship. So that means those two variables work in the opposite direction. So if pressure increases, our volume is going to decrease. Or if pressure decreases, our volume is going to increase. They're moving in opposite directions. Okay. Charles' law is a relationship between volume and temperature. So V1 over T1 equals V2 over T2. And this is an example of a relationship that varies proportionally. So they move in the same direction. If volume increases, so should temperature. If volume decreases, so should temperature. We also talked about Gay-Lussac's law, which is pressure and temperature's relationship. P1 over T1 equals P2 over T2. This also is a proportional relationship. So as pressure increases, so should temperature. As pressure decreases, so should temperature. Okay. And all these laws can be summarized by P1 V1 over T1 equals P2 V2 over T2. That's the combined gas law. Now, you don't have to memorize each of those individual laws if you know the combined gas law, potatoes and vegetables on the table. Okay, so for example, if you're looking for Boyle's law, we know that that's pressure and volumes relationship. If I ignore these two T's down here, I'm left with P1 V1 equals P2 V2, which we know is Boyle's law. Okay, so the combined gas law is probably the one that you want to know, and that will help you know each of those individuals' relationships as well if needed. Okay. Now, one last relationship that we want to talk about is how volume and the numbers of moles are related. Now, what we need to think about is what's a mole? A mole is telling us how many particles there is of something, right? So it makes sense that if we have more moles of a gas, that gas should take up more space. Okay? Essentially what we're saying is if we have more moles of something, we have more molecules of something. And if we have more molecules of something, those molecules are going to take up more space. So volume and the number of moles also vary proportionally. The more moles, the more volume, the less moles, the less volume. Okay? It's going to be like those the majority of our relationships where we see them changing together. Okay? This relationship is even more fully explained by something called Avogadro's theory. Avogadro should sound very familiar because we've been talking a lot this year already about Avogadro's number. What this law says is equal volumes of a gas, if at the same temperature and same pressure, will contain the same number of molecules. Now, this is a lot different than solids and solutions that we've talked about so far, where we couldn't use volume to determine how many particles there is if we were only given a volume. Okay, so for example, if I want to know how many moles of sodium chloride are in a sodium chloride solution, if I only know I have a liter, that's not going to tell me anything because I need to know what the concentration is to be able to figure out moles. Gases, because there's such big spaces in between each individual particle, we can actually assume no matter what the gas is, if it's at the same temperature and it's at the same pressure, doesn't matter if it's carbon dioxide gas, oxygen gas, nitrogen gas, they are all going to contain the same number of particles if it's the same volume at the same pressure and the same temperature. So what's neat about this is we can actually use our mole ratios like we've been previously using to convert between moles, to convert between volumes of gases. Okay, because we can assume they have the same number of particles if at the same pressure and temperature. So how we do this is through something called a molar volume. Now, a molar volume is the volume occupied by 1 mole of gas at a given temperature and pressure. Okay? It's kind of like molar masses, but for a gas and for any gas at a specific pressure and temperature. For example, a mole of oxygen, a mole of carbon dioxide, and a mole of hydrogen gas will all take up the same amount of space as long as all of those gases are at the same temperature and the same pressure. So if I have a balloon of ammonia gas and helium gas and oxygen gas, if all of these are at the same pressure and temperature, they're all going to take up the exact same number of space. It doesn't actually matter what gas it is, it just matters that the pressure and temperature is the same. Okay. So we can use this, like we use molar mass, to determine moles of a gas from a volume. Okay? Each pressure and temperature is going to have a unique molar volume, just like each element on the periodic table has a unique molar mass. Okay? The two that we should know, and the two that we're going to use most commonly, are SATP and STP. So remember, standard ambient temperature and pressure, 25 degrees C and 100 kilopascals. Or standard temperature pressure, so 0 degrees C and 101.125 kilopascals. So this formula should look very similar. It's essentially what we used to do for molar mass, but instead of saying moles is mass divided by molar mass, we're going to say moles is volume divided by molar volume. Okay? So I'm going to make myself disappear so we can do some of these questions together. It says, how many moles of a gas are in a 2.13 liter helium balloon at STP? Now it gives me the molar volume of a gas at standard temperature pressure of 22.4 liters. So what would we do? We would say, well, if I want to know moles, I'm going to take my volume and divide it by my molar volume. Volume is given to me here, 2.13 liters, and my molar volume is given to me. This is a constant, 22.4 liters a mole. Okay? Now, keep in mind, it doesn't matter if this said helium or oxygen gas or ammonia gas. Doesn't actually matter the gas as long as it's a gas. So this piece of information isn't actually even important. Any gas at STP is going to take up 22.4 liters as if it's 1 mole. Okay. So now, just like molar mass, I'm going to take this 2.13 and divide it by 22.4. That's going to give me, and I'm going to report this to 3 significant figures because we have a 3 here and a 3 here. So this is going to be 0.0951 moles. Okay. Which makes sense. It should be less than a mole because a whole mole would take up 22 liters. We only have about 2 liters. Okay. If this was a question on a test or a quiz or an exam, you would likely get a mark for your formula, a mark for showing your work, including your units, and a mark for your final answer, including units, and again, significant figures, now that we know how to report significant figures. Okay. Here's another question. It says, what volume is occupied by 0.024 moles of carbon dioxide gas? Again, what gas this is doesn't really matter. Could be O2, could be nitrogen gas, doesn't matter. It's any gas at SATP. Now, the molar volume of SATP is 24.8 liters a mole. So do the same thing. Moles is volume divided by molar volume. My moles is given to me in the question here, 0.024 moles. I don't know the volume, that's what I'm asked to calculate, but I do know the molar volume at SATP is 24.8 liters a mole. So to get volume by itself, I'm going to multiply both sides by 24.8 liters a mole. 4.8 liters a mole to cancel this out and get volume by itself. So volume would be 24.8 liters a mole multiplied by 0.024 moles. That's going to give me And I'm going to report this too. This has got 2 significant figures, and this is a 3, so I'm going to report to 2 significant figures. 0.60 liters, and it's going to be in liters because molar volumes is in liters per mole. Okay. So this is all well and good, but one thing that we do have to be aware of is that all the calculations we have done so far make the assumption that we're dealing with something called an ideal gas. Okay. So what's an ideal gas? An ideal gas is a hypothetical gas that obeys all of the gas laws we've learned so far perfectly under all conditions. Okay? So pressure and volume always are going to follow each of those laws exactly. Okay? Each of those relationships we saw, it doesn't matter the conditions, they're always going to follow those relationships perfectly. The problem is, in real life, there's actually no such thing as an ideal gas. There is no gas in existence that follows all of those laws perfectly under all conditions. Okay? I'll tell you why. First thing is, an ideal gas has particles that take up no space. Well, there isn't a gas in existence whose particles take up no space. They take up a very small amount of space, so it's a pretty safe assumption and it's a safe model to use, but there is no gas that whose particles take up no space. And an ideal gas has particles that have absolutely no attraction to one another. And we know gas particles, like any particles, will have van der Waals forces and they will have at least a slight attraction. That's how we can condense gases down into liquids, like with liquid nitrogen. Okay? So we use these laws assuming that we're dealing with an ideal gas, but in fact we can't be, because there's no such thing as an ideal gas. There's no gas in existence that actually is an ideal gas. And this is why. An ideal gas would never condense into a liquid when it's cooled, which we know real gases do. And it must perfectly graph those relationships between pressure, temperature, and volume we learned earlier in the week. And they would have exactly linear relationships. Now, we see that the relationships are pretty close to linear in most cases, but there are places where those relationships sort of vary off a bit in extreme conditions. So we can still use these laws because it's a very good model, but know that it's not a perfect model. Okay, there are some scenarios in really cold temperatures or really high temperatures or extreme pressures where the model that we're using may have slightly less accuracy. Okay. Now, sometimes we're not changing between two conditions like we've been looking at so far with a P1 and a V1, a P1 and a P2, or a V1 and a V2. Sometimes we just need to know what's happening with a gas in a specific state that we're in. In that case, what we would often use is something called the ideal gas law. The ideal gas law, what it is it's an equation that summarizes the characteristics of an ideal gas. Okay? So what we would use, how we calculated that, is using something called PV equals nRT. That's the ideal gas law. Now, P, like we've been doing so far, measures our pressure. Now, it's really important that your pressure is in kilopascals for this question. Okay? The V is volume. Also really important that your volume needs to be in liters. N, we should know, is moles, which is in moles, not surprisingly. T is our temperature, which is in kelvins. And R is something called the gas constant. Okay? The gas constant is kind of like Avogadro's number. It's a number that doesn't change. It's 8.31 kilopascal liters per mole Kelvin. Now, if you Google the gas constant, or R, okay, for gases, you're going to see that you may actually find different numbers. Now, what's important though is that the units are really important. In our class, and what's most often used is the gas constant that's in kilopascal liters molars Kelvin. You could look up the gas constant for atmosphere, milliliters, moles, degrees Celsius, or atmosphere, liters, moles, kelvins, like you could change these variables, but what is a lot easier in my experience, just know 8.31 instead of memorizing a million gas constants for slightly different units. Just memorize 8.31 kilopascal liters per moles Kelvin and make sure that your units are always kilopascals, liters, moles, and Kelvin. Okay, that's a lot easier than having to switch and look up a new R value for every single time you do the calculation. Okay. So R is the gas constant, 8.31 kilopascal liters per mole Kelvin, and like we said, it's a constant of variation that relates pressure in kilopascals, volumes in liters, moles in moles, and temperature in kelvins of an ideal gas. Okay, it's a very good measure that we can use. We do know it's not perfect because there's no such thing as an ideal gas, but it is a really good measure. Okay, but like I said, really important that if you are using the ideal gas constant, or the gas constant, that your pressure is in kilopascals, your volume is in liters, your moles are in moles, and your temperature is in Kelvin. Okay, let's take a look at how we would use this. It says, what amount in moles of methane gas is present in a sample that has a volume of 500 mils, a temperature 35 degrees Celsius, and 210 kilopascals? So this is when we're going to use PV equals nRT. Now remember, we said volume needs to be in liters, temperature needs to be in kelvins, and pressure needs to be in kilopascals. So good news is we can use our pressure as it is, but we do need to still convert our volume and our temperature. So we'll start off by converting my temperature. We know we have to add 273.15. So let's put that in my calculator. This is going to give us 308.15 Kelvin. And we know 500 milliliters, we've been doing this a lot, is 0.5 liters. So now all of our variables are in the correct units. So let's plug it in. Our pressure is 210 kilopascals. Our volume is 0.5 liters. Moles, we don't know what moles is. That's what we're trying to calculate. R is always going to be the same, 8.31 kilopascal liters per mole Kelvin. That's the units. And write the units every single time because we know we always have to write units after a number. And also, it'll remind you every time you write it that to double check is your pressure in kilopascals, your volume in liters, your moles in moles, and your Kelvin in kelvins, your temperature in kelvins. And our temperature is 308.15 Kelvin. Now to get moles by itself here, we're going to divide by 8.31 kilopascal liters per mole Kelvin. Kilopascal liters per mole Kelvin to get rid of this. And then we need to get rid of 308.15 Kelvin. Okay, get rid of this. So our moles is going to be 210 kilopascals times 0.5 liters divided by 8.31 kilopascal liters per mole Kelvin and 308.15 Kelvin. Now, all of these have been reported to 3 significant figures. So I'm going to report this to 3, so I'll put in 210 times 0.5 divided by what's on the bottom here. So we said 3 significant figures, so we have 0.0410 moles. Okay, so that's the amount in moles we have of 500 mils at 35 degrees Celsius and 210 kilopascals of methane gas. And again, this gas could be any gas, it doesn't matter, but that's the gas that was given to us in this question. Okay, well, let's do one more. It says what mass of neon gas should be introduced into an evacuated 0.88 liter tube to produce a pressure of 90 kilopascals at 30 degrees Celsius. So we're going to use PV equals nRT again, but you may say, hey miss, it's asking for mass, and there's no mass in that formula. That is true, but keep in mind we do have moles in this formula, and we know how to convert between moles and mass. So we're going to be using some of our understanding back from Unit 3. So let's put this in. Our pressure is in kilopascals, so that's good. We're going to put in 90 kilopascals. Our volume is in liters, so that's good. 0.88 liters. Our moles we need to calculate. Our R, 8.31 kilopascal liters per moles Kelvin. And our temperature is given to us in degrees C, but we need it in kelvins. So you're going to get really good at converting between these two. Okay, so now we'll put in 303.15 Kelvin. Now we need moles by itself again, so we're going to divide both sides by 8.31 kilopascal liters per mole Kelvin and 303.15 Kelvin to get rid of these guys. Whatever we do to the left, we have to do to the right. Okay. So it's going to give us moles 90 kilopascals times 0.88 liters divided by 8.31 kilopascal liters per mole Kelvin and 303.15 Kelvin. So moles is going to give me 0.031 moles. Now, it didn't ask for moles though, it asked for mass. So I'm just going to say, well, I know moles is mass divided by molar mass. About that. Moles is given to me, I calculated 0.031 moles. My mass isn't known, but because it's a neon gas, I can look that up on the periodic table. It's molar mass, which is 20.17 grams per mole. So to get mass by itself, I'm going to multiply both sides by 20.17 grams per mole to get this by itself, which means mass is going to be 20.17 grams per mole times 0.031 moles, which is going to give me and I'm going to report this to two significant figures because each of these values in my question have two significant figures. So it's going to be 0.63 grams. Okay. So I'm going to have you practice some questions here. You have 5 questions from your textbook. Again, keep in mind that if you're having any problems, you can reach out to me via email. You can check in with me on my office hours, or you can check our FAQ page, which has some solutions for some questions that our students are commonly having a little bit of trouble answering. Okay. Otherwise, hope we're all staying safe, staying healthy, and staying at home. Look forward to hopefully seeing you soon. Bye-bye.